Hello.
A little bit more, please.
Um, okay. Hello, everyone. I am Abby Zhang, and I will be presenting a mobile camera system to assist in better posture through computer vision and artificial intelligence.
Can you increase
So,
the volume a little bit? Can you be a little bit louder, please?
okay, hold. Is this better?
Yep, it's perfect. Thank you.
Okay. So, I will go over, I will first go over the problem, our solution, then the methodology, experiments, user feedback, future developments, and our conclusion. Okay. So maintaining a strong and upright posture is very beneficial to the long-term health of people by reducing the risk of muscle tension, pain, and fatigue. It also helps develop a proper posture, um, improve balance, enhance the physical physique, and create a better mood. However, many students and adults around the world are known to slouch when working at their desks for hours on end. Statistics have reported to show that out of around 600,000 students, 65% of children and adolescents were deemed to show incorrect posture, and around 3.7% were referred to radiology. Moreover, students will potentially worsen their posture over time, leading to severe damage to the spinal cord, which then results in several joint and degenerative diseases such as multiple sclerosis, arthritis, Parkinson's disease, etc. Other studies have shown that posture worsens as age increases, and in addition, it's evident that the generation today is already at risk, and so this problem may affect future generations in the long run as our technology becomes more advanced and prevalent, and students gradually increase their intake of computer usage throughout the years. Previous studies support this by showing that students have a direct correlation between the number of musculoskeletal problems with the number of hours on digital devices. One study revealed that 70% of students ages 10 to 12 years old reported musculoskeletal symptoms in at least one part of their bodies that are tied back to their usage of computers. Therefore, a solution that can improve various people's posture to ensure that their overall health will be stable and healthy for decades will be discussed in the following slides. So to solve this problem, we propose to use a device connected to a camera to analyze posture. This proposal solves the problem of bad posture because it alerts users to straighten their spines whenever they are slouching. And to do so, we incorporated AI into a camera system that allows it to identify the slope of the back or the spine to determine whether or not you are slouching. Users will have a mobile app that can keep track of their statistics and notify them to straighten their back. This is an effective solution because it uses persistent monitoring that tracks the user's movement throughout the time it is turned on. This allows for a long period of working with good posture and is effective in the long term. Furthermore, the statistics and data contained in each recording enable users to identify their trends and progress. Due to this, they can make adjustments on their own accord if necessary. Ultimately, this proposal is an innovative and efficient way to improve your posture and health through a simple push of a button. So there are three main components making up the experience for Posture Guide, which is the mobile app, an optional Raspberry Pi, and the analysis pipeline. The mobile app allows access for users to monitor themselves through the Raspberry Pi's camera module. The AI analysis process is what measures and calculates the user's posture to determine whether or not they need to engage in better posture. This is connected to the Raspberry Pi camera module, which is the device that will record and view the user. The intended flow of the user is to create an account in our app, then choose their preferred method for monitoring setup, which is using either their phone camera or a separate device camera, and then learning from the information our application provides to determine any fixes in their posture. Overall, this program uses Flutter to develop the app, Python for the Raspberry Pi, and MediaPipe as the analysis component. And so the analysis process works by taking in a video feed and then feeding that information into a get pose function where the loaded model can analyze the frame to get pose information. The draw landmark and the fetch posture slope functions in turn visualize the results and also determine if the user is exhibiting good or bad posture by checking the various angles between landmarks of interest, such as the hips, knees, back, and shoulders. In the home screen, we implemented a live view that can be accessed through the phone or a separate camera module. And essentially, how we did this was that a Raspberry IP address was determined when setting up the device. It is used to allow the app to connect to an HTTP endpoint that allows us to view the video stream within a widget. You can also click into the widget to start recording your progress, to which the recorded clip will save in the gallery down below. The Raspberry Pi is the core computer powering the device prototype that accompanies the app, which monitors the user before analyzing the feed and notifying the user if they have bad posture. If the user elects to use this device, it will handle setup and connection completely headless. The Wi-Fi characteristic class is part of a large code base that lives within the Raspberry Pi itself, which allows it to be remotely given the Wi-Fi information so that it can connect to a new network. This is necessary as the video feed is streamed to an HTTP connected to the local network for other devices to view. If the Raspberry Pi determines that it is not connected to Wi-Fi, it spins up a Bluetooth server that our phone can connect to and provides the Wi-Fi information from the mobile app itself. Once this information is retrieved, the Bluetooth server will attempt to connect the Wi-Fi network and respond with the IP address so that a connection can be established. So for the experiments, there were a number of factors that we are seeking to investigate, two of which include the lighting and the camera angles. To test each of the various factors and their impact on the overall system, we isolated each of them in their batches for tests. And for each batch, the control runs were the user operating the system under ideal conditions with both good and bad posture, while the experimental runs applied a variation relevant to the factor being tested. Ideal conditions can be defined as generally good lighting, with the camera directly facing the subject with all of the subjects visible without any obstructions. Currently, through these trials, we found that the AI was most accurate when the room was brightly lit, with a percentage of 87%, while moderately lit had a percentage of 82%, dimly lit with 73%, and of course, no visible light with 0. In the camera angles, we found that the control, which is the side view from the right, had an accuracy of 87, the left with 85, um, and the left front diagonal with 75%, right front diagonal with 77%, left back diagonal with 45, and right back diagonal with 56%. Another potential blind spot in our program is the plethora of user experiences, perspectives, and impressions that could have possibly been affected through external elements. By collecting their experience, there could be further improvements made to enhance this product. For this experiment, feedback from the users was collected after providing the application and necessary equipment and allowing them to use it throughout the week. The survey itself was designed to gather information both about the user's posture history and also the means through which they interacted the most with the system. We look primarily at comfort derived from posture, as well as the subject's ability to focus in terms of impact. There's also a field where respondents can provide general suggestions to allow for a more nuanced picture of the experiment. In the beginning, we collected that 14 users were phone users while the other 6 were device users. This gave us general insight on the relevance and popularity of either options, which could potentially help us with future developments in this project. In the feature requests that showed us the various feedback that user has provided, and we intend to analyze and use this data to improve our overall system, app, graphics, and other aspects to offer the most optimal experience for them. Now, let's take a look at other studies and solutions surrounding posture, their effectiveness and their limitations, and how it influenced our solution. Firstly, a study conducted by Lauren Simpson, Monish Maharaj, and Ralph J. Mobbs examined the role of wearables in spinal posture analysis. Wearables are basically technologies worn on the body and measured step count, heart rate, sleep quality, and other parameters. They are shown to have the potential to monitor posture to prevent further neuromuscular consequences using biofeedback. The accuracy of these devices was high with error ranges with 5 degrees of the mean capturing moments. However, their biggest challenge remains in the lack of validation, as most reports only experiment on small samples of these devices over a short period of time. In addition, the practicality of these technologies could also be questioned. They require an optimum number of 3 sensors for an accurate reading of posture analysis data. With multiple sensors attached, this may pose a challenge for users to remove and reattach when needed, reducing the practicality of it. In contrast, our project, only requires the user's phone camera or a Raspberry Pi camera module to use. Another study was conducted observing hip positioning and sitting posture through the use of a pressure sensor tied to a hip positioning algorithm. The system they developed can accurately locate hip angles and pressure values to classify four types of sitting postures. This is done using a support vector machine with a polynomial kernel and can achieve an accuracy rating of about 89.6%. This study also targets the need for better posture guidance to improve chair ergonomics. The one disadvantage here is that their solution required a custom array of sensors that the user needs to sit down on, which is not as readily available as a smartphone or a small portable device like what we are proposing. Lastly, researcher Wang took a more general approach to the problem by discussing the overall design of intelligent products for sitting posture correction. They point out how improper sitting posture can also indirectly cause myopia. A research report from the World Health Organization shows that in 2020, the number of global myopia patients is about 2.5 billion. The initial device prototype they show off is a Lego EV3 model that the user straps to various parts of their body to gather positional and posture data paired with notifications and reminders. This is similar to our approach of sending reports and reminders for people with bad posture, with the main difference being that we are pushing for a computer vision-based system that does not require the user to strap anything on them. Um, Multiple limitations are present in this project, and we can start with the software limitations, which mainly fall under the issue of speed. This is because between every frame of the live stream, there is some amount of time that must be spent identifying the landmarks and analyzing the data. This creates an issue for a live feed, as spending too little time would result in accurate results, while taking too long would result in laggier looking video streams. The implementation of a faster landmark would also be something in the future that we would be looking to develop. Um, a faster landmark detection model combined with a more sophisticated implementation of the analysis algorithm given the landmark data can help further improve the usability of the system without compromising on accuracy. A small periodic stream delay could also be employed to give the live feed enough time between processing frames to give a smoother playback when the user is briefly viewing them. Lastly, general hardware improvement that can be made on the hardware side is through the use of an IR light combined with a camera capable of perceiving it. Infrared light is invisible to the naked eye, but can help provide illumination for a camera even in the dark. Of course, this particular improvement applies more to the dedicated device, although a small add-on accessory for a phone could be an option to consider. In addition, minor adjustments could also be considered. For example, the camera module or phone must be mounted on a high enough platform, otherwise it will be difficult for it to view and analyze the user. Furthermore, sufficient lighting is also recommended for improved clarity and quality for the recording to support the accuracy of the AI. In conclusion, our solution serves as a valuable tool for enhancing and promoting optimal posture habits. Through the ever-improving AI, this solution can contribute to long-term posture improvement and overall well-being with its simplicity and accessibility. Ultimately, incorporating this product will become increasingly relevant and contribute to a health conscious community. Thank you for listening to my presentation. Are there